So good morning, everyone. Thank you for inviting me over, and I'm happy to share our research work on efficient model extraction attack from counterfactual explanations. And I'm Hangwei, and I'm currently a scientist at Center for Frontier AI Research in Singapore. So it's one of the newly established research center in A*STAR, which is like a national level research center in Singapore. So here is the table of contents. I will share some research background first, and then I will talk a bit about counterfactual explanations as well as model extraction attacks. And then I will introduce our proposed DualCF, and finally the conclusion and some takeaways. So as we all know that deep learning models nowadays are getting bigger and bigger. And it's also driven by more and more data available from different sources. And to deal with such large quantities of data, we need to design more and more complicated models with larger computational capacity. But with the development of such larger deep learning models comes the problem of the development of by ourselves. So developing such kind of high-performing machine learning models become more and more expensive because we need very large computational resources, and also the data is not free. So in this case, the machine learning as a service platform appear, and it's attracting many users. So this kind of machine learning as a service involves two parties. The first party is the cloud service providers, and the second party is users. So for the first party, the cloud service providers, they launched these machine learning as a service platforms, and they use the data they collected or gathered or annotated for training a large model on the cloud. And then these pre-trained cloud model are served in a black box way to the users. And for the users, they can have access to these kind of cloud-based models remotely by public APIs. But the cost is should be paid on a pay-per-query basis. So basically, all kinds of applications with automated decision-making can be used in these machine learning as a service platforms, including healthcare, recommender system, finance, and even other applications like school admission or job admission, and so on. And so for each user, as shown in the figure here, they can upload their query by X1 or X2, and then the models in the cloud side can return the prediction output fx1 or fx2 to the users. And of course, the API can be customized. So basically, it can output different types of prediction outputs. For instance, the majority of the prediction or the probabilistic views of the prediction of fx1. And also, there are two other types of outputs that APIs can provide. The first one is the gradients, which can reveal some information on the model itself. And the other type is the counterfactual explanations, which is our research interest. So we will explain later. But with additional information provided by the APIs, basically the cloud model turns to be more vulnerable to model extraction attacks. So there is a trade-off for these service providers, whether to have more public accessibility or to focus more on the model confidentiality. Because if the cloud model can have more public accessibility, basically more users would like to use the system because it's more powerful. But on the other hand, when revealing too much information of the cloud model, so basically users or other adversaries maybe can replicate the cloud model. So it's quite dangerous for the service providers. Okay, so how these counterfactual explanations be useful? So let's see an example here. So let's say the application is the loan application to a bank. So the bank can have its own database for its customers, and it can train a black box machine learning model on the cloud service. And then if this model is equipped with the counterfactual explanation, then it can provide more information to the user. For instance, if the applicant submit his application by representing his personal information as X, and then the bank may return the output as rejection, because in his personal information X, it may contain the low salary or the low credit score of this user. But for the user side, he wants to know what he can do to improve his status so that for the next time he applies, maybe the bank can approve his application. So the user is more interested in how to improve his own status so that the current system can change the prediction of this model. So in this way, the counterfactual explanation C here is basically can be seen as a modified version of his input X. And in this application, this C may look like increasing the salary by 500 or increasing the credit score by 100. So basically, counterfactual explanations answer the question of what minimum changes are needed to flip the current prediction. And for a given data point X and a black box model F, it wants to find a data point, which is called counterfactual explanations C. And this C should be close to X because if we want to change from X to C, we should pay some cost or certain debt or something. And in this way, we use the D measurement to measure the distance or the cost function to measure the changes between the X and C. And such that the output of this counterfactual explanation point C equals to Y, which is the desired outcome. And this desired outcome, FC or Y, is not equal to the original prediction F of X. So in this way, counterfactual explanations can reveal the reasons behind the current prediction made by the current cloud model. And also it can reveal the minimal changes required to flip the prediction. And usually in real-world applications, users are more interested in changing from an undesirable prediction to a desirable one. For instance, to change the unhealthy situation to a healthy situation, or to make the loan application from rejected to approved, or from no offer to offer, and so on. And also, we can add more constraints for these counterfactual explanations based on our practical needs in our real-world applications. And the two commonly used constraints are actionability and plausibility. So actionability refers to the situation where some features cannot be changed. For instance, the age of the applicant, or the gender or the race of the applicant. So in this case, the counterfactual explanation C should be restricted in a subspace A. And for the plausibility, it refers to that the counterfactual explanations should lie within the original data distribution, such that in this way, the founded counterfactual explanations have meaningful explanations in the real-world situation. And also, there are more constraints, such as diversity, sparsity, and causality, based on different situations or applications. Okay, so let's come back to the model extraction attacks. So basically, with such powerful cloud models in place by the service providers, there are many adversarials that aim to steal these cloud models' functionality to build their own substitute model, such that they can use the substitute model to bypass the cost required for the query, or they can also provide the substitute models to other users to make profit by themselves. So basically, if we term the cloud model F of theta, so the aim of adversarials is to construct a substitute model H equivalent with parameters phi with high fidelity of the cloud model, such that the substitute model should mimic the internal function of the cloud model. And for this kind of the attacks, basically, we will assume that the adversarials or the users cannot have access to the training details or the architectures or the parameters of the cloud model. And also the data should not be accessible. But the users or the adversaries can obtain the data format or some basic profiles of the APIs, such as the number of the classes that this model can support. And also users can collect a set of samples to query multiple times. So under this assumption, so there are basically two state-of-the-art approaches for model extraction attack, as shown in the figure on the right-hand side. So the first one is still machine learning model. So basically, it's the most original one. And so it's upload original query X and get the feedback f of X. And then with a large number of queries and predictions, this still machine learning model can approximate this cloud model's format. And the model extraction approach basically use the additional counterfactual explanations C, as well as its prediction F of C as additional input when constructing the substitute model. But still, it also requires a large number of queries because for the adversaries, they don't know the distribution of the original data and they don't know the internal functionality of the model. So they need a lot of queries and the predictions to mimic the function. And for this research direction, model extraction attacks with counterfactual explanations, and in terms of the security and privacy issues, basically researchers do not come into a common sense of the issue. So some researchers think that these counterfactual explanation methods can allow users to receive explanations without convey the internal logic of the cloud model. So these two references are from the year of 2017 and 2020, so it's not very old. But the second viewpoint is that counterfactual explanations can reveal the internal logic of the cloud model. So it can leak very important information of the cloud models. And these two references are not very old as well, from 2019 and 2020. So here we want to propose our method called DualCF. And our goal is to significantly reduce the number of queries required to steal a cloud model F of theta. And in this way, we also want to make sure that this substitute model H of phi should be in high fidelity. So it should mimic the original cloud model F of theta. And then we have the query set denoted as D, and also an evaluation set of denoted as T. So we want to make sure that on this independent evaluation set T, our substitute model H of phi should have similar performance or similar prediction as the original cloud model of theta. So the objective is to maximize this indicator function among the evaluation set. And the constraints is that the functions, the two models, should have the same prediction on this query set D. And also for these counterfactual explanations, their predictions should also be the same. And we want our method to be simple but efficient. And our method is motivated by the observation on the decision boundary shift issue of the current extraction approaches. So let's see what decision boundary shift issue is. So here we see 4 figures, and so let's focus on the first one. So in this figure, we have 2 colors represented 2 different classes. So the blue one represents the data points from class 0, and the purple data points represent the data from the class 1. And this black line here is the ground truth decision boundary of the cloud model. And here, if we upload a query, which is denoted as the orange dot here, and then this cloud model can return the counterfactual explanation as shown in the green triangle. So with this one pair of data, so basically the decision boundary learned by the substitute model can be shown as the blue dashed line here. So basically with one pair of data, this model extraction method can achieve about 77% of agreement. So agreement is like the maximum is the 100%. So the higher is the better. And here, so the issue is that we do not know the ground truth decision boundary, and we do not know the underlying data distribution. So maybe for another user, they will have a different query as shown in the second figure here. So for this query, the orange dot is placed in another position. And in this case, the counterfactual explanation founded is on the other side of the decision boundary. So in this case, for this user, the corresponding decision boundary is shown in the blue dashed line as well. So we can see there is a lot of variety existing for different users or for different queries. And moving from the second figure to the third figure, basically if we use more queries, here we use 9 orange dots, and then their corresponding counterfactual explanations all lie within this decision boundary of the cloud model. So with more counterfactual explanations available, basically the decision boundary of this substitute model can mimic much better than the previous 2 situations. So this agreement come to 94%. But with our DualCF approach, we want to make sure that we use as few queries as possible, and also this decision boundary should be closer to this ground truth decision boundary. So we can see that when this data distribution is unknown, which is practical, so this issue existed for all the situations, and this issue is more severe when the query size is very small. And also, as observation, the random queries can be far away from the decision boundary or can be close to the decision boundary. But the counterfactual explanations generated by the cloud model are always close to the decision boundary. So in this case, the counterfactual explanations definitely reveal certain information of the cloud model. And the decision boundary of the substitute model tend to move towards the middle area between the query as well as the counterfactual explanations. So we just wonder, is it possible to find proper queries such that we can use very small number of queries to mitigate this decision boundary shift issue? And our answer is yes, and we find a very efficient way. So basically, we leverage the information that, or the fact that counterfactual explanations are always located in the close to boundary regions. So in this case, when the queries are closer to the boundary, so basically the shift of the decision boundary should be alleviated. So in this case, given a query point, the orange dot here, we first upload it to the cloud model to get a counterfactual explanation. And then with this generated counterfactual explanation, we reuse it as another query. So we get the counterfactual explanations of these counterfactual explanations, and we term it as CCF, and we denote it as C prime. So basically, we have two queries. The first query is the input, and the second query is the counterfactual explanation C. And we get two counterfactual explanations, C and C prime here. And both of them are counterfactual explanations. So both of the data points lie very close to this decision boundary of the cloud model. So as shown in the figure on the right-hand side here, we have green triangle as the counterfactual explanations, and the red dot as the CCF or C prime here. So you can see that basically with one pair of CF and CCF, we can locate the decision boundary in the nearby area very precisely. And then with these pairs of CF and CCF, we can train the substitute models. And in this way, we can just alleviate the unknown data distribution problem existing for the original query strategies. So as a comparison, so basically the training sets for different model extraction approaches are different. So for the still machine learning, its training set is the X and the FX. And for the model extraction, it's the original one with the additional counterfactual explanations and its prediction C and FC. And for DualCF, we don't use the query itself, and we use the C and C prime pairs. But also, if we use the original query, we come to our variant of our model, where we call DualCFX. And also, we conduct some theoretical analysis for this for our proposed method, and I'm not going to elaborate here. But one conclusion is that for the simple situation where the cloud model is a binary linear model f theta, we can extract a subsystem model with 100% of agreement from just a single pair of CF and CCF. So for the experiments, we compare with the above baselines, and we implement both models as multi-layer perception models. And they have the same architecture, but they have different render initializations. And we run 100 runs for fixed query sets. And we measure the metric use agreement. And here we generate two synthetic datasets, one with linear decision boundary and another one with nonlinear decision boundary, and also 3 real-world datasets. And we split the dataset into 3 sets: the training set, query set, and the evaluation set. So the query set is maximum of 25% of the original data, because for baseline method, they tend to use more queries. But for ours, we can just use a subset of this query set. And after training, the experiments are evaluated on the evaluation set. And here is the illustration of the experimental results on the synthetic datasets. So on the first figure, we have 3 queries dotted as green dots, and 0, 1, 2 here represents their query sequence. And with the query, different models can obtain different outputs, like the triangle, the counterfactual explanations, and for us, we have the red dots, CCF. So for the still machine learning approach, so we can see the subsystem model's decision boundary has a certain angle with the original ground truth decision boundary, and agreement comes to 85%. And for the model extraction, with the few number of queries, basically the angles between the 2 decision boundaries are still very large, and agreement is about 86%. But for ours, with only 3 pairs of queries, we can arrive at the agreement of 89%. And here is the overall experiment on the 5 datasets. So basically, the first row represents the agreement, and the second row is the standard deviation of the model. So our model is shown in the purple and the orange for our model and the variant. So we can see that basically our variant, this DualCF, can achieve the best performance on these 5 datasets. And basically our DualCF is the second best one. And with respect to the standard deviation, ours are much lower than the other baselines, such as this red one, the still machine learning. So in conclusion, these counterfactual explanations definitely reveal useful information of cloud models. And existing model extraction attacks suffer from the unknown underlying data distribution issue. And therefore, they require large number of queries to train a better subsystem model. But for our DualCF, we leverage the fact that counterfactual explanations are close to the decision boundary. And then we use this counterfactual explanation as additional query input to the cloud model, such that our proposed method can effectively reduce the number of queries required. So basically, that's the end of my talk. Thank you.